In elementary grades, you may have studied a simple pendulum. The formulas that we derive for simple pendulums in elementary courses is only valid for small angles. What if you decided to swing a pendulum by some angle like 80 degrees? Then you can no longer use the formulas that you learned in your earlier classes, but you must start from scratch. So let's write down Newton's second law for the simple pendulum. It is the sum of all the torques about the pivot point is equal to the pivot point P over there is equal to the moment of inertia of the pendulum times the angular acceleration of the pendulum about the pivot point. So if I write this out, because the torque is negative, the R cross P, the R cross F rather, the force of gravity is this way, that's R cross F is into the page, and into the page is negative, so I'm going to get negative mg L sine theta, and that's equal to the moment of inertia of the point mass, which is just ml squared, assuming the pendulum's radius is really small, times the angular acceleration, which is the second derivative of theta. We are using here Newton's notation of dot, meaning time derivative. The mass of the pendulum does not matter. One of the factors of L also cancels out. And I'm going to get theta double dot plus g over L sine theta is equal to 0. G over L is sometimes called the natural frequency of the pendulum, omega squared. This is what you would get if the pendulum angle were really small. If here we assume that theta is really small, then I get theta double prime double dot plus omega squared theta equals 0, and that leads us to simple harmonic oscillation, and so you get omega, which is equal to 2 pi over the period, and that's equal to square root of g over L, and that gives us the famous simple pendulum period formula, 2 pi square root of L over G. So that's what you get in your elementary grades, but that's not what we're interested in. We're interested in solving this complete equation. How do you get any further without making the approximation that theta is small? Well, the way you do that is to proceed by a series of steps known as the first integral. The first integral of this is to find out what the theta dot would be. We're going to use a trick by Newton. So I multiply both sides with theta dot. So I get omega squared sine theta theta dot equals 0. Now if I integrate both sides, actually there's one more step I can write. I'll recognize that this is nothing other than the derivative of theta dot squared, because the derivative of theta dot squared is 2 times theta dot times theta double dot. That 2 cancels with a 1/2. And then if I do this, omega squared, I can write that as negative cosine theta dot equals 0, because the derivative of cosine theta is negative sine theta, but because I've put a negative sign there, that goes away and I get theta dot from the chain rule. So in a sense, we have already done the integration. This is called the first integral. So I get 1/2 theta dot squared minus omega squared cosine theta equals constant. That constant is a constant of integration that needs to be determined. So we can take that when I release the pendulum at some specified angle of theta naught, the pendulum was not moving because that was when it was released. So that's the initial condition I can use. At theta equals theta naught, the point of release, theta dot equals 0. So that gives me, if theta dot is equal to 0, that's going to give me the constant is equal to negative omega squared cosine theta naught. So that gives me the full expression. Let me write that down. 1/2 theta dot squared. I can bring this over the other side. So I get omega squared cosine theta minus cosine theta naught. So I can solve for theta. As a matter of fact, I'll get two solutions because theta squared is given. So theta will be plus or minus of this thing. Now because the pendulum has been drawn like this, I take the negative solution since it's going to decrease the angle. So the theta dot is in fact 0, less than 0. So I get theta dot is equal to negative square root of 2 omega square root of cosine theta minus cosine theta naught. Now theta dot itself is d theta over dt. So I can solve for dt next. So dt is going to be negative d theta over this whole thing, root 2 omega square root of cosine theta minus cosine theta naught. And if I take the integral from 0 to t being the time it takes to go from the top to the bottom, that gives me theta naught to 0. 4 times this is the period, because period is time taken to go from here to here, then here, then here, then back. So 4 times this time is the period. Let's just focus on finding this integral first, because multiplying it by 4 times is not a big deal. Let's do the following. Let's write cosine theta as 1 minus 2 sine squared theta over 2. And we'll do the same thing for cosine theta naught. And then let's make the following substitution. It seems awfully opaque right now why we do this, but it'll become clear to us when we get any further. So this makes the value of x lie between 0 and 1, because theta cannot be bigger than theta naught, and it can be as small as 0. So that's great. Then dx will be 1/2 cosine theta over 2 d theta divided by sine of theta naught over 2. So if you make these substitutions, then you'll end up with the integral from 0 to 1. You lose the minus sign because of this. I'll flip this limit. That will lose the minus sign. Okay, so integral 0 to 1, 1 over omega, the root 2 is still there, and d theta is going to be all this stuff. So I can write this as d theta, I can write as 2 times dx, because that 2 comes over there. Then the sine theta naught over 2 also comes up here. And then I get cosine theta over 2. So let me write that. But cosine theta is just square root of 1 minus sine squared theta. So I'll write it like that. And then I also have the square root of cosine theta minus cosine theta naught, but I'm writing it like that. The 1's cancel out, and I get a further square root of 2 from that. Now because this minus sign is there, I'll be switching the order of theta naught and theta when I do this. So that you may think, oh wow, that looks pretty complicated, but notice the 2 cancels out because there are 2 root 2's, and so this 2 cancels out. Is this any better than what we had before? Well, I'll tell you why it is better. Because this is 1 over omega integral dx over let me try the following. I'm going to take out from this sine squared theta naught over 2. If I do that, those two things will cancel out, and I get 1 minus sine squared theta over 2 divided by sine squared theta naught over 2, which is just x squared. So if I do that, I get square root of 1. This is just 1 minus sine squared theta naught over 2 times x squared, because I'm writing sine theta over 2 as sine squared. Sine theta over 2 as x times sine theta naught over 2 is what I'm doing here. And here, what the process I just explained, I take out the sine squared theta naught over 2 to cancel it with the numerator, and then I get 1 minus sine squared theta over 2 divided by sine squared theta naught over 2, which is just x squared. Well, the advantage in writing it like this is actually a very famous integral known as the elliptic integral. So elliptic integrals play a big role in mathematics. The elliptic integral I'm referring to is known as k of u. K of u is called the Jacobi complete elliptic integral of the first kind. So just like the close encounters with aliens, you have the first kind, the second kind, and the third kind. And in my opinion, it's less scary to meet aliens than these elliptic integrals. So k of u is actually integral 0 to 1 dx of the square root of 1 minus u squared x squared square root of 1 minus x squared. That's why we struggled so hard to bring it to this form. If you bring it to this form, then your life is set. You just have to go to the tables of elliptic integrals and start looking at what the answer is. So this is basically 1 over omega times k of sine theta naught over 2. If I say it's 80 degrees, then it's going to be sine of 40 degrees. Find out what sine of 40 degrees is from your calculator. Then go to the table of elliptic integrals of the first kind and look up what k of that value is, and you're done. You have finished the problem. Now, I'm not interested in looking at tables, but I want to do this integral in a more sedate fashion. Suppose I want to write it as an approximation of a number of terms. Can I do this integral without resorting to tables? The answer is to some degree yes, but I'll be writing it as a infinite series. So what I'll try to do is keeping my, this is elliptic modulus is sometimes called k, so let me use little k instead of u. So that's elliptic modulus k. In our case, k is equal to sine theta naught over 2. So what I'm going to do is I'm going to assume that k is really small. If k is really small, I can expand this as a Taylor series. So 1 over the square root of 1 minus k squared x squared can be written as 1 minus k squared x squared to the power minus half. And I can write that as 1 plus negative half negative k squared x squared plus higher order terms. Let me just focus on the first order term. Okay, the higher order terms are done in the notes. So I'm going to end up getting this integral that I have to evaluate is going to be the integral I is the integral from 0 to 1 dx over the square root of 1 minus k squared x squared times the square root of 1 minus x squared. And I'll say it's approximately equal to the integral from 0 to 1 dx over the square root of 1 minus x squared times 1 plus, because the minus and the minus become plus, k squared x squared plus higher order terms, which I won't bother with. Alright, because I'm omitting the higher order terms, I put this approximate sign. Let's try to figure out what this is at least. What I can do is put the substitution x equals sine psi. Then dx is going to be cosine psi d psi. When x equals 0, psi will be 0, and when x equals 1, psi will be 90 degrees. So this gives me a good way of converting this integral. So I get I equals the integral from 0 to pi by 2 dx, which is cosine psi d psi, over this thing, which is square root of 1 minus sine squared is also cosine psi. So lo and behold, that disappears. And then I just have 1 plus k squared sine squared psi. So that's not too bad. In fact, the first integral, term 1 is just pi by 2. And the second term is actually k squared, there's a 2 here, I forgot, over 2 times 1/2 the beta function of 3/2 and half. The reason I want to go ahead and write it in terms of beta function is because this makes it really easy. Now actually if we do the next term, it'll turn out to be like this: 3k to the 4 over 8 1/2 the beta function of 5/2 and half. And each time you go higher, this half will remain the same, and the beta function here will go up by a number 1. So next term is going to be 7/2, and this is going to be k to the 6th. And then you're going to get k to the, and that's going to be, instead of 3, 5. And the next term is going to be 7, and that's going to be k to the 8. And here, instead of 8, you're going to get, next term is going to be 16, and then you're going to be 32. So it's very predictable what these terms are going to be like. I can write a few more just by pattern formation. The reason I'm showing you this is because it's very easy for you to take the higher order terms. Now, by the way, pi over 2 is what you expect, because pi over 2 omega is the quarter period, but 2 pi times over omega is the full period. So pi over 2 omega is the quarter period. But all these correction terms you get are very predictable, and each time you get this beta of two things, you can use a functional identity of beta of nm is equal to gamma n gamma m over gamma of n plus m to simplify it. So basically the problem is doable to any degree in accuracy of the elliptic modulus k. And in this way you can solve problems, if not exactly, at least approximately to any desired order of accuracy.